and train my ML models. Let's say support vector regression is one of the algorithm typically used for the design optimization. Okay. Now I have a simulation input also, output also. I'll train the model. From the training, I'll get an idea of future importance. Out of these 12 design variables, which are the important design variables? First, I will narrow down. Let's say the 12 variable to 2 variable I narrow down. Okay. From the 2 variables, now I'll make a design simulation case. I'll put it into the actual FEM simulation to see the weight reduction without compromising the strength. If it happens, okay, I'll again feed back to my ML model. Again, go for one more iteration to find out is there any best other possible cases. So conventionally, if I do 20 iteration, now I will end up with only very few iterations, less than 5. Okay, so only 5 different combinations I will finally do with my fine mesh simulation to arrive at the lightest possible bracket without compromising the strength. Okay, this is one of the typical example for surrogate model. Okay, means like I have some data, I will train my ML model. I'll use it for some other applications. Okay, so only 5 designs need the FEA check. So ML pre-filters what are the bad things which I should not do the simulation, waste my computation time and cost. So my 75% time or the effort is reduced. Okay, and how do I evaluate any ML model? There are some metrics. So for example, R square. If R square is equal to 1, is the perfect prediction is equal to reality. And R square equal to, let's say, 0, it's a very poorest fit. So it's a fitment of your regression equation. Usually, accuracy is understood by R square. Now, as I said earlier, where ML can play a important role, one is the design. So one example, I showed you a design example. Second is discovering the new material. So one of the question was there in our chat box. How do I use ML for new material discovery or new composition discovery? We'll take an example case. My objective is in 600 series, that is aluminum, magnesium, silicon. This is the aluminum alloy family. In that family, can you figure out the composition, optimized composition of magnesium and silicon in aluminum alloy, which will leads to me high strength aluminum alloys in 6 series. Okay. So for this, I can pull out the data from literature about 1000 samples with a 6 series composition, and typically T6 treatment is applied, that is solution treatment and aging. So that is my sample, and my output is what I desire is highest strength, highest hardness with good ductility, because both are opposite in nature. So I need to have a target which is in a compromised state, with which is very important is for me is the strength is very important. So my UTS should be as high as possible with a good amount of ductility, let's say about 10% ductility. So how to solve this problem? First, I'll take these 1000 samples. Let's say 60-40. 600 samples I use it for training, 400 samples I use it for testing. So typical algorithm we use is a random forest model. So I'll talk about all these algorithms, what is it at a later point of time. Because as a mechanical engineer or the material engineer or people who are not from computer science, their job is not to understand what is ML algorithms and how it works. Their job is to understand how I will be using ML for my work, where all ML can do something significant contribution in my area. Once we understand where I can apply ML, next step is what are the ML algorithms are there, which one I should choose. And the second part of it, you don't need to do it by yourself. You can also seek the support or the collaboration from actual computer science engineers, because they will give you the latest update on the algorithms and help you to figure out right algorithm for your data, provided you explain them very clearly. What is your input, what is your output, what parameter you are trying to optimize it, or what you are trying to detect it. Okay. So when I have this kind of input output scenario where I want to maximize a certain output parameter with little compromise on another output variable, uh, and which I don't know, because see, if I take it aluminum, magnesium can vary from 0 to let's say 30 volume percentage. Silicon also vary from 0 to 30. Aluminum can vary from 0 to 70, let's say. So how many combinations are there? I may need to make thousands and thousands of combination of chemistry to find out what is the best chemistry. Chemistry will give you UTS and harness, which is not practically possible. So in that case only, Bayesian optimization will come into help. I mean, from the 1,000 samples, it will make one new best experiment. It will give you one composition, and you have to again go back to the lab and make the composition and test it. If it is coming good value, again feedback to the model. Next best experiment it will give you. So likewise, you can go for the reaching the most optimized composition. So for example, what Bayesian optimization will do in the first training, it will try to understand what is the influence of magnesium and copper. Increasing magnesium will increase the strength, decreasing the copper increase the strength. So it is more of exploiting the existing data. Then it will also look for the area where in the data set unexplored area. Then it will take the exploitation result and exploring result and give us the highest chance of improvement area. That is the best combination. So for this case, it suggested 5 new compositions, out of which one composition has given 420 MPa. Typically in aluminum, magnesium, silicon alloy, you get to 320 MPa. So you can understand, like, how to discover the new alloy composition or the new alloy by using the machine learning without putting much effort. Because when I have lakhs possibilities, how do I arrive at only 5 possibilities? From the 5 possibilities, one possibility will be the best one. So what is the advantage I get is reduced experiments. And what is the root mean square error? What is the possible error will be about 15 MPa. And what is the benefit I'm going to get? The discovery of the new alloy, the time taken to discovery of the new alloy is reduced by 6 months. That's the biggest advantage I get. Now, all these mechanical or materials who are sitting over here will understand what is this Bayesian optimizer, optimization, or random forest. See, these are very simple mathematical, based algorithms which we can understand by just looking at the algorithm flow. So we don't need to put too much brain onto that. Only what we have to understand which scenario, which algorithm to be selected. That's all our job is to do that. And now all the algorithms codes are already written by the people. You have to just take and import into your you have to take the your data set and import it to the PyTorch or some kind of Jupyter kind of a platform where already ML algorithms are there, and select the ML algorithm. It will do the optimization and give you the end results. So it is like this, like, to put it very simply, I don't need to understand what's happening behind the Excel sheet. I need to understand what are the options are there in the Excel, like say functions are there in the Excel, or which way I have to sum it up the tables, kind of futures available in the ML, available in the Excel. I have to learn the similar if you draw the parallel in ML, I should know what are the algorithms are there. If you ask me, based on my best of my knowledge, I understand about you have 30 different types of algorithms, and under each algorithm you'll have branches of some 10 or 50 algorithms. Okay, let's say you take it decision tree. There are about 20 algorithms will be there. Let's say you take it random forest. Random forest associated algorithm maybe 10 will be there, but all of them will work more or less similar with a little bit difference in terms of the accuracy and the predictions. Okay, but if you look at it, what is a different type of algorithm? Hardly you'll find 30 or 40 distinct algorithms. If you know that groups, that's more than sufficient for as to select the arrive at the group. From the group, then we can select some algorithm and explore it for our data set. And there is nothing called this is the algorithm will be used for this set of experiments. For example, new alloy discovery, you cannot just say that we can only say random forest family and Bayesian optimization family we can use algorithm. We cannot concretely or pinpointedly say this particular algorithm only will work well. We cannot say, because it depends on the data set and the variability in the data inside. Whether the data set is wide or the narrow, okay, and kind of numbers it handles, whether it's only handling the numbers or image also. So with that it varies. Third one, most important application of ML in our mechanical engineering is, let's say I run a spindle in CNC machine. I just wanted to know when it will fail or when I should undertake the maintenance before it breaks down. So it's a typical case of prediction before it fails. That's a predictive maintenance. So we in CNC machines we have sensors and which will pump a lot of data, especially the vibration signals like fast Fourier transform spectrum, cortices, envelope peaks. So these are my inputs, and the operating conditions, the speed at which it rotates, and load acting on it, what is the temperature, and these data are already recorded by the sensors. Let's take the data of 10,000 hours operational log, both normal and faulty. And since it's a time series data, like with respect to time, the data signals are varying. So there is a RNN based algorithms which will handle very well time series data. Okay. So in recurrent neural network, there are models like LSTM is one, long short term memory neural network on time sensor network. So I'll take that, I'll import that model, I'll import my all data, and my model objective is to predict the remaining useful life, let's say from based on the data, and also to help us to understand at that point of ours what is my health score of my spindle. If it is 0, okay, it's going to fail. If it is 1, just newly fitted spindle. So job is to predict the remaining useful life of the spindle and health score. So that's what my ML model will do. So there is a algorithm what I told you, like LSTM is used. Predictive accuracy for the present case is about 87%. If I use different algorithm, for example, the random forest, if I use it, it's 72%. Okay. So how it's going to help me? The downtime is reduced 40%, maintenance cost is reduced 25%, and most importantly, I don't have any accidents or any surprises or shocks due to the premature failure, because everything is based on the data. I analyze it, and I very well predict about 30 to 40% residual life time only. I'll come to know that okay, I should be a little more careful. Anytime spindle can go into failure mode. Okay, so this is another practical case where we can use the ML in the industry. Right. So next is can ML replace simulations or experiments? This is one of the pertinent questions all the core engineers we have. So far we have been using ANSYS, Abacus, kind of a simulation for my studies, or CFD simulations, and I do experiments. I'll get a lot of insights from the experimental data. With ML, can I do away with these two? If you ask me, it is not at all possible, because ML is just a supplementary to the existing experiments and simulation. It's not the replacement. Okay, it can serve as a additional surrogate model to approximate your FEM or CFD kind of simulations by narrowing down the simulation cases, reducing the simulation time and cost, a computation cost. And ML doesn't follow any law of physics. Okay, just a purely mathematical tool. Whereas your simulation packages or your typical real experiments, you follow the law of physics. What ML can do, it can take this simulation data or the experimental data, get trained, and understand the hidden pattern. It's more of the pattern recognizer, which we human beings or the simulation may miss. Okay. So the bottom line is ML cannot guess physics on its own without data. What it can do, let's say, we have seen the case of bracket. Instead of doing 1 lakh simulations, it can narrow down to, let's say, a 50 or 100 simulation to predict the your end outcome of reduced weight without compromising the strength in the previous case. So all these, supplementary exercise will help you to reduce the time you spend to design and optimize and reduce the computation cost. So it's not a replacement, it's a supplement. Okay. So this you should have in your mind. And how do I integrate with these simulation packages? There are Python APIs and scriptings. If you know that, we can just get integrated with our simulations. I mean, you don't need to export, import business, you don't need to do that. You can have along with your ANSYS. Now ANSYS itself has come up with the AI models, ML models inside. Okay. And most of the engineers, we think like ML, we talk about it. Like typically, if you see computer science engineers, they use it for the consumer data or fault finding or fraud, detections, kind of areas where they use where there is a voluminous of data. But in my sphere of mechanical and materials engineering, to do your experiments only, I will take long time and money I have to spend. So am I affordable to use ML for my work? And really, how many number of data are required? A simple regression cases where input output you wanted to understand the relations, just 100 data is sufficient. And if you really want to do the deep learning, where you work with the images and trying to understand, like for example, defect classification or the microstructure faces identification kind of a image, this one, minimum 1,000 samples are required. Then in that case, you may think 100,000 sample means it is impossible, because for me, I can do hardly 2 experiments or 3 experiments. So how I can get this many number of data to do realistic ML? So there are ways. So one way will be collecting the existing historical data from the literature and work on it. Of course, historical data may not be available for a particular case where all the input conditions remain same, because each person would have used a different combination of the chemistry or heat treatment practices or different machining processes. Data may be there, but all will be different in nature. So in that case, I cannot use the historical data, you may say. Agree with you, but there are ways. There are different type of MLs are available for us. One is the transfer learning, another one is physics informed machine learning. These two doesn't seek more data from us. Okay. And there are ways and means to create the synthetic data, meaningful synthetic data, and there are ways to have active learning. This all will help to solve the problem of data scarcity in our mechanical engineering. Okay. We will see this one by one. Okay. So before I get into these 4, let me go back to the window of messages and see. So far, I think I have given you very few information about what is ML. Let me also understand any other questions are there and any things are correct. Okay. So needs for advanced material, latest corrosion test and use in the paper and testing places. Okay. So these questions what you are asking now are not related to the ML, but I will definitely address you. What are the latest corrosion test and use in paper and testing place? Okay, where it can be tested. Journal paper where it is used. Fine. So kindly feeds questions. So let me read. What are your other questions? It may be relevant to ML or may not be. I do understand that most of the mechanical engineer hate the computer and digital. But unless we don't adapt to that, future will be very, very difficult for us. As you can see in your admission nowadays. So I'll give you a 2 to 3 minutes break to feed your questions, feed your thoughts on ML, and what you want to further learn. so that accordingly I will speak. I'll just give you a 2 minutes break for all of you. Are you able now? Yeah. Now, okay, fine. So, what I understand from the audience, I think most of them are just for the attendance they have joined. I think so. Very few have asked the questions. I lost the chat box also. Can you please put it back again? To answer one of the questions, what are the different type of optimization techniques are there? So I'll share the slides and explain you. Hope the slides are seen. There are four types of machine learning algorithms are used, and I'll get detail into that in the subsequent slides. So please acknowledge whether my voice and slides are seen. Hopefully. Hope my voice is okay and you're able to see. Can someone unmute and speak when it is in need? Actually, I know that. Yeah, fine. So, yeah, yeah. There's a one question on what are the different type of optimization and techniques. So, as an core engineers, there are four ways we can use our ML for our work without huge data. One is the active learning. Okay, so what it does is with a minimal sample, it will do the maximized learning, and it will intellectually or intelligently tell you the sample strategy to get the to design the most informative experiments. I know it's a highly technically jargon. I will give you example in active learning on all the four cases in the subsequent slide. Second will be, let's say I take a model and I train the model for titanium. I have a data set and a titanium. I can adapt it for other alloys, like for example, aluminum alloys. It's called the transfer learning. What the ML model does, it will try to understand the generalization of the alloy behavior. Only those information it will take it. So in the, let's say I have trained my model in titanium alloys, where it understands that strength is proportional to the universally proportional to the grain size. Let's say that understanding it will take it. And when it goes to the aluminum alloy, if you have very minimal number of data, it can easily fine tune and try to get you the output in a very narrow domains. Third will be, you can have the physics law also embedded into your machine learning model to get the realistic learning, and it reduces the data need. So I'll explain you everything in subsequent slide. Fourth will be, model itself will learn and adapt to the new scenario or the new situations with very few samples. So these are the four type of ML activities we can do it for our work. What are those? We'll take example case by case. I have a, let's say, a gear. I want to predict the fatigue life, and each fatigue test will take about 1 week. And let's say I take an example of 7075 aluminum alloy, aluminum zinc alloy. I cannot do, its strength is 550 MPa. I cannot do fatigue test from 200 MPa to 550 MPa, and number of cycles from 0 to 10 power 7 cycles to get the actual graph. It means I need to do thousands and thousands of samples to get the fatigue curve as well as the endurance limit. And again, it is for the one situation, or futures means input. Let's say for one stress and number of cycle conditions, 7075 one configuration, I need to do 1 lakh samples. Let's say I vary the mean stress, I vary the heat treatment of the alloy, I vary the grain size. You can understand 1 lakh experiments into number of variables. That many number of tests I have to do. But hardly I can do 20 tests or 15 tests. I can have a small data set. So how in this scenario, I can predict the fatigue life? What actually our ML will do? Let's say I take an example of random forest algorithm, I use it. The model try to, look at the region, which is the uncertain stress regions, where it is not very sure if the part will, fail in 10,000 cycle or 1 million cycle. Then it only recommends new experiments only in that stress level only. As I said, like 100 to 550 MPa, it will try to figure out the endurance limit area. Let's say it's 300 to 350. In that domain only, it will suggest you the mean stress and stress amplitude and ask you to do the test to find out number of cycles it endures. So what it's trying to help us is to avoid the efforts on the regions that model has already understood well, like 100 to 300 or 400 to 500 MPa, that range. It is knows very well one is a low cycle region, another is high cycle fatigue region. So this is a transition region only, it is not very clear where it will material will find. Okay, so these regions it will help you. So you can call it, this is active learning, which will help you to narrow down number of experiments to very few instead of many random experiments between 100 to 550 MPa. So finally, you get a beautiful fatigue SN curve. Okay, and you can check whether whatever the fatigue curve it gives right or not by doing certain experiments and figuring out model parameter characteristics like root, mean square, error. Okay, so the simple way to understand, it saves a lot of time, month of testing and 70% of the cost. So this is one way we use the active learning. Second is the case study. Let's say now additive manufacturing is the buzzword, and the cost of the material is very high. Printing cost is high, testing cost is high. Okay, let's say in that scenario, industry wants to know, wants to detect the defects coming in the 3D printed parts with a very small data set. How it can do? There is one more way, one more method in our mechanical engineering or in the machine learning is a transfer learning. Learn from X person, apply on the Y person. Here,
அந்த செல்ல எடுத்துருக்கோம் பெரிய செல்ல
so it is the responsibility of the organizer to chop off the rogue elements who have joined today. Please do that. So in the transfer learning, let's say in the casting manufacturing process, I have voluminous of data, X-ray images, radiography images, 50,000 images, I'll take it. I'll train my models. And I'll also take some few data set from the 3D printed material, like let's say titanium 6 aluminum 4 vanadium. All of them I put together, I train my model, I validate my model to detect porosities, lack of fusion, and keyhole porosity. That is my objective. So there are already available algorithms are there, like CNN algorithm, like ResNet. There are many algorithms, CNN algorithms are there, mainly for the image-based one. Can you please unmute that person or remove from the group? No, it would be good for everyone who are listening. I'm getting a lot of noise from that person. Fine. So now in the transfer learning, I learn from the castings, I apply in the 3D printing. Similar manufacturing process because defects more or less same it comes. So I have a pre-trained model in the casting data, fine-tuned with the 3D printing data. So the output will be tomorrow I make a 3D printed part, I'll get the X-ray scan. I feed into the ML model, it will classify the defects, what kind of a defect is there, and what is the fraction of defects, size of the defect, all the information we can through a trained model we can get it. But I train the model using the casting data mostly. Only I have 10% of the 3D printed data, but still I achieve the accuracy of 92%. So the performance is, there is a less need for the large AM data sets. And aero industries, there is a quick adoption because of this transfer learning. It helps in the quality assurance of any aerospace companies who adopt the additive manufacturing. So this is the second model people use it, transfer learning. Then I talked about organizer, please can you help me out with removing that person who is not understanding the things, simply as joined for disturbing us. Yeah. So third is the physics informed machine learning. That is one method, optimization method. How does it used? If you see, how is it used? If you see the objective, let's say I take an objective of a quenched steel, and I just wanted to know in a gear from top surface to the core how the hardness is varying. Okay, this is what I want to predict it. And I know the material is steel, which consists of carbon and which is heat treated to the quenching. There is a cooling rate, and this material has certain grain size. So this information I have as an input. Some 50 steel sample data only is there. Okay, only 50 is there. So there is a algorithm. This I want everyone to note. Physics informed neural network. Most of our cases, even one of the question on crystal growth, they also can note down this because this neural network has a provision to include the fundamental physics rule equations, physics or chemistry equations. For example, in this case, hardness, how it varies. Only is grain size is the one variable. Carbon content. If higher the carbon content, higher the hardness. So logic way. And higher the cooling rate, grain size will be smaller. So you will get the high hardness. And higher the carbon also, the molten state hardness increases. So what are the relevant physics equation? If you see, when you have elements, there is a diffusion. So carbon diffusions are diffusion is usually uh, predicted using the Fick's law, mass transfer law. And if I want to understand the transformation, phase transformation kinetics, like with respect to temperature and time, what I have used for my heat treatment, what kind of phases forms, and what is the fraction of phases forms, especially non-equilibrium phases like Martin-Save binates and all. There is a equation JM-AK law. So that law can be incorporated into my neural network. So output, what I will get from my ML model is hardness with respect to distance from the surface to the core. What is the depth of hardness at each locations? Okay. This physics informed neural network, how it works, you cannot understand. But what literature says, it's much better than the black box ML. The error typically you get from your output is about 10%. But most importantly, it captures all the real physics. Okay. So because we integrate physics equations into ML, so our predictions are more realistic. It is not like a data depending on the data, because garbage in is garbage out. That's what typically told in ML. If my data is good quality data, then I'll get the good quality output. If my data is noisy, has outliers, has missing values, kind of bad quality data I have, my predictions also accordingly, my error will be very high. But one advantage with this physics informed ML is I integrate the physics law and I minimize the data requirements. So my end results will be much less error prone with better predictability. The last one is learning from learning. That is a meta learning. Let's say I have been using my lathe for machining a titanium alloy. Suddenly I bring the inconel alloy. I just want to understand the tool wear. Before putting the inconel alloy, I have done a few inconel alloy machining. So in this kind of a scenario, meta learning will help. Learning from the past learning. So predict the tool wear for new materials. Let's say I used the steel or aluminum or titanium alloys in my lathe. Past data set is there, and I have done very few, machining of inconel 708 super alloy. Now, how will be my tool wear? That is what my objective. So we can use the model agnostic meta learning method or the machine learning method. What it does, it learns from the past machining problems, which has happened on steel or aluminum or titanium alloy. Okay, which is quite opposite to your normal ML, where you need a lot of data every time when a new material or process are studied. What it does in this kind of a MAML, it quickly adapts to the new material, that is the inconel subunit. So it will give a output as a tool wear curve. So you just need only 5 to 10 tests instead of 100 plus machining operations. The accuracy is close to or more than 90%. Okay, by predicting the tool life, of course, it will help you to reduce the experiments by 80%. So what we are, in summary, if you put it very simply, I trained the model on many related tasks, machining of different materials, and try to predict the newly come, materials influence on tool wear. So when a new material comes, the model knows already the general rules of tool wear applies here. With just a few test samples, I can quickly adapt to the new scenario and predict the tool wear. That's all. So these four are very important, which you have not heard about it. Most of the classes, if you go, what people talk about it is, this is what the people talk about it. So one of the question also was that, what are the different algorithms are there optimization? This is a general bookish information. If my task is a classification, like for example, I want to classify the defects or the phases, we can use the classification ML algorithms. if my task is to predict something, let's say a property, fatigue property, or strength, or hardness, or ductility, then it's a regression-based ML models are used, or even you can use the artificial neural network. If I have my input as an image, like the microstructure is one of the things, or you do some X-ray CT scan, so you'll get an image. So when I want to work with the image kind of a data, people use CNN, convolutional neural network. Suppose I have a data which is a time series data. So one of the example we have seen a few minutes ago, wherein I have a data time series data for the vibration from the vibration sensors. Okay. So, or other words, one of the question was the new corrosion tests and other things. So this corrosion or wear or fatigue or any robotic control system, these all are time dependent. Like with respect to time, you generate the data. So when I want to work on these kind of data sets, recurrent neural networks are used. For example, vanilla, LSTM, one of the case I showed you, long short-term memory, okay, and GRU, back propagation TT. So these kind of different algorithms are there. We have to see the data set accordingly. We have to select, or you can select 2-3 algorithms to see which gives a better accuracy. So broadly, if you say ML is used for either supervised conditions of the learning, where I know what is input, what is output, the labeled data are there, or unsupervised. I know the cluster of data, but it is not labeled. Or I can also use it in a scenario where reinforcement learning takes place. For example, trial and error, more of a reward based one. It will go if Optim is better, it will get rewarded. If Optim is bad, it will be unrewarded. Kind of a reinforcement learning also it can be used. So to answer that question, different type of classification algorithm you can see on the left side and the application on the right side. So there are about 7 to 10 algorithms are there, which are very prominent in the classification. I think you would have come across support vector machine, logistic regression, rainforest. Again, these whatever the information I have given are typically found in literature, but doesn't mean that if you are working on the defect classification, you should use logistic. You can try logistic, support vector algorithm. These are the K nearest neighbor. These are prominently used in this kind of case studies. Similarly, in the regression, there are about 7 to 8 algorithms, either linear, polynomial, lasso, elastic net regression, a multi-layer perceptron. So each one has certain applications, like our mechanical property predictions or fatigue life predictions, thermal conductivity predictions, or all your properties like wear, tribology, corrosion, estimations, or any properties which has a non-linear behavior. I wanted to estimate it. Inverse material design, like you have certain amount of material composition, certain condition of material composition, arrive at something else back, or you have a property and arrive at the right composition to achieve that property. It's inverse material design. And suppose you have a microstructure image or the X-ray CT scan image, a different convolutional neural network, we can use it. So these are already inbuilt and developed by the computer science people. Our job is to only pick up and fit into our model data. What this CNN algorithm it will do, when I have let's say a microstructure image, it can segment the microstructure and part it into the different feature and extract the features, like what are the regions where I have martensite phase or austenite phase. We can extract the details. We can delineate the grain boundaries. Okay, so likewise we can do the analysis by using the this kind of algorithms. Okay. Similarly, I have a recurrent neural network like time series data, which I talked about in fatigue or creep or wear or the corrosions. These are the time dependent phenomena where I have a data with respect to time. When I want to analyze this data, I can use various RNN algorithms, ARIMA, DeepONet, LSTM, Bayesian optimization, Gaussian process regression. Likewise, there are many algorithms which will suit to my requirements. And one of the questions on the optimization, there are optimization algorithm to find out the most optimized parameter space, genetic algorithms, simulated annealing, and differential evaluations. So when I work on the design optimization problem or topology optimization problem, where we can use this. And you would have heard about particle swarm optimization, ant-colony optimizations. These are used for when I work with the material composition or the process parameter optimization. When I work with the manufacturing process like 3D printing or the welding, I want to optimize certain control parameters. I can use a reinforcement learning. So these slides I will share it with you to have a understanding on what are the different kind of algorithms are available for what kind of applications. Okay. So these are the typical algorithms. There's one slide which I wanted to show you how a typical ML workflow is. You need to have a data set. You need to clean the data set, remove the corrupted data, outliers, fill the meshing values. So once your data set is clean, you can just put it in the Excel and see the visualization of it. Whether do you need ML or not is the first question you have to answer. Let's assume that you are unable to figure out through the Excel what is the kind of a pattern I get in the data. Okay, then I can go for the ML. Then try to look at the data's range. Any outlier is there, please remove it. Any class imbalance problem is there, try to clean it up. Then let's say I have 7 variables, out of which 3 variables are interrelated. So first you take the data, do the future map. That is called future importance. Future means input importance. Let's say 7 variables, out of it 7 variables. What are the important variables? There is a case where composition, carbon increases, ultimate tensile strength increases, yield strength increases, fatigue strength increases. So what it implies, typically strength increases if carbon content is increases. So all the 3 will definitely increase. So all the 3 are interrelated. So I don't need to have all the 3 variables. I can have only one, either OS or UTS or a fatigue limit. So this is called future importance to reduce the number of features which we consider for ML. And when I have a data, let's say a X, Y, Z are input, X ranges from 1 to 10, Y ranges from 1 to 1000, Z ranges from 1 to 1 lakh. Okay. When you have this kind of a widely varying, narrow and wide range data set, it is better to normalize the data so that your data lies between 0 to 1. So when I do these all the operations, then only you have to go for the model selections. Once I select the model, I have to bifurcate my data into training and testing. Again, in the training, I have to do the cross validation or cross folding. Let's say I have 60% of the data. That data also 60% also I should have different folds. Like every time I should train my model with a different data among that 60%, so that I can make my model to learn from the data rather than memorizing from the data. Okay. So that is called the training phase. Then you have other 40% of the data or 30% of the data to validate it, to understand your model how accurate is. Once you understand your model is 95% accurate and your job is done. This is the typical ML workflow. Okay. So what are the softwares you should know? Tools, scikit-learn, TensorFlow, PyTorch. Okay. And if you are a material engineer, MatMiner and Materials Project APIs. These are the domain-specific tools available in the internet. You can explore it. So please understand, when your data is complex, you are not able to make any sense out of it, go for ML. If your data is very clearly seen as a linear trend, or you can stick with your conventional method. No need to go for ML. Okay. So I'll take another 5 minutes to just tell you what are the funding schemes are there in India which you should know, so that when you're working in ML or other disciplines, as an academician, you are expected to now show the research output for your institution. Mainly institution wants NIRF ranking or NAC NBA kind of accreditation where this research component plays a vital role. In order to be a more productive researchers, first you should know what are the funding schemes available in India. Okay. And these all the funding schemes currently promote AI and ML because AI/ML is one of the mission by the government of India. Okay, this is identified domain by the principal scientific advisor to the Prime Minister. So if you look at the funding landscape in the country, Anusandhan National Research Foundation, that is ANRF, DST, DRDO, ISRO, Response Basket, CSAR, Department of Atomic Energy, Department of Scientific and Industrial Research, Indian Council for Social Science Research, EICT. These are the bodies typically fund for academicians research. Again, research grants, you can classify to two category. One is the basic research, another one is the applied research. So if you are interested in basic research, where your end result will not be any product or the applications, that comes in the basic research, where you are trying to propose some theory or discover some new phenomena. So ANRF has a grant modes, advanced research grant, Prime Minister early career research grant, for socially underprivileged community like SC/ST, inclusivity research grant. Can you put mute? Thanks for testing my patience. PAIR is one more scheme. If you are working in theoretical sciences, matrix, um, state university research grant, teacher associate research grant. So these are the grants are available in ANRF. Coming to the DST, SIST is one scheme where even MTech graduates can apply, people who have not done PhD. And AICT has research promotion scheme that is also helps supports basic research. So all of these funding agency fund about 60 lakh rupees for minimum 3 years project. Okay. Doesn't fund only for science and engineering, it also funds for social science domains and cross-disciplinary and interdisciplinary. Especially currently AI and ML is given more importance. And coming to the applied research grant, when I mean applied research means if you're taking in the DRDO project, it should have defense application. ISRO means space and DIE means atomic energy. So likewise. So looking at the DRDO, there are 4 research boards: armament, aeronautical, life sciences, naval. As the name suggests, armament means guns, tanks, bombs. Aeronautical means aircraft, helicopter, UAV, drones, missiles. Life sciences means anything related to the military personnel, soldiers. Naval means submarines and ship. These boards have a panels, and if you go to that board, there are panels about 6 to 8 panels. All the 8 panels, if you explore, it covers all the engineering and science department. And recently, DRDO has started DRDO Industry Academia Center of Excellence at few IITs. They also fund for Tier 2 institutions. And DRDO has one extramural research body and technology development fund to support the startups as well as organizing the conference. Coming to the ISRO has a Response Basket program where they detail the program problem statements. You have to give the solution. So this is another funding body. DST has multidisciplinary, multi-institutional calls called IRHPA, and Indo, other country. You take it Indo Taiwan, Indo Bhutan, Indo Sweden, bilateral calls. Time to time it comes. Department of Atomic Energy has a project proposal scheme called BRNS. Okay. And Indian Council for Social Science Research, under the major project and minor project, they fund for social science related problems which can use the technology like AI and ML. So these are the funding schemes in a research project wise. Okay, there are some funding schemes exclusively for the women researchers, where men are not eligible to participate as even a co-PA. So SERB have power scheme. DST has Vice, Kiran, Vidusi, Scope, and Curie. All of them are schemes. And if you look at Corely, all these schemes have a age limit up to 60 to 62. And they have also categorized institution into category 1 and category 2, where category 2s are private institutions. So that you don't have men competition, you don't have a IIT, NIT kind of a premier institution faculty competition. So, and the age limit is also 62. And most importantly, throughout the year you can apply. So these are exclusively designed scheme to empower the women researchers to get into the research. And Department of Scientific and Industrial Research also has a scheme, A2K plus TT, TT, UPW kind of schemes exclusively for the women startups. And they also fund for travel to publish a paper in abroad in the conference through Wing scheme. Recently, UK and DST has jointly launched the program called Women Leadership Program to train women researchers as a leaders, like a VC principal, to take up the VC and principal kind of a roles in the academic institution. They designed the 1 week program to empower them with the leadership skills. Faculties who are doing PhD, please look at Karyashala Ritika program in SERB. That will help you to get you the hands-on training or the intern at IITs. And AICT has launched the PG certificate programs in emerging technology. Mechanical engineer, I advise them to go and do the cross-disciplinary, especially in the circuit branches, so that you can sail through in a situation where currently you are facing a recession in your branches. Because these current branches of mechanical civil will not sustain for long. Branches will exist, but the kind of number of colleges where we have number of seats, these many seats may not get filled. So unless you don't occupy and come out from your comfort zone, like how the software companies where people who have learned Java those days got a job, then the advanced languages come. Unless you don't learn, you are left in the race and you will be fired. Same scenario currently is existing in the education sector, especially the private engineering colleges. Unless you don't upgrade, migrate to the domain which is of market need. I don't say it's a good or bad, because every field is good, but there is a market demand for certain courses only or certain field only. So out of which AI and ML will be ruling for next 10 years. So try to obtain the certificate. Once you obtain the certificate, irrespective of your branch, you are eligible to teach in other domains. There are INSA visiting scientist program for the faculties to go to IITs and learn something. And there is a summer intern given by IIT Delhi every year. There is a leadership program for all the faculties given by IIT Jammu. And if you're interested in startups, look at the Nidhi scheme and Prism schemes. If you want to do the postdoc, Inspire and Nehru Science, these are the best postdoc available in the country, which pay you very good as a stipend. For PhD, PM Fellowship and US India Entrepreneurship Fund Fellowship. And if you wanted to organize any event in your college, under the ANRF there are schemes. AICT there is a scheme. CSER lab there are schemes. Domain specific, like if your conference focus on space, ISRO funds. DRDO under ERIPR there's funds. Indian Council of Agricultural Research or the medical research, they also fund in the agricultural and medical regions, medical research areas. And if you wanted to organize the, if you want to travel in government money to present your paper or have a short scientific visit, there are schemes in ANRF, AICT, DRDO, similar like all the institutions. So this is mainly meant for the to travel as well as event organizing in your college. Okay, with this I just want to close because time is around 8 o'clock. So this is my contact details. I run a broadcast group wherein I try to help all the faculties in the research and sending them the informations, like kind of a research calls, opportunities available for them. If anyone interested to join, send your name, department, your research area. So I will save, I will include you. I'll send information which may be useful to you or may be useful to someone else. If it is useful to you, use it. If it is not useful to you may be useful to someone else, please forward to others. So don't expect me to customize the information and send it to you. That's just I'm doing for a purely social service to benefit the faculties, because I believe you are the one who are going to set